Hello everyone, my name is Yuncheng Wang. I'm a PhD student from the Institute of Information Engineering, Chinese Academy of Science. Our work is automated flow detection for industrial robot REST service. Industrial robots are mainly composed of three parts. The first is a manipulator, such as the orange machine on the left of the right image. Then there is a controller, which is an embedded device. Finally, the programming interaction part is used for field control or offline programming. Industrial robots are applied across a wide range of critical industries. They are often used in collaboration to create automated production lines, such as those found in automotive manufacturing, electronic assembly, pharmaceutical production, and logistic sorting. According to the 2023 World Robotics Report, the number of industrial robots in worldwide has exceeded 3.9 million units. Since industrial robots are a critical component of production lines, the downtime of a single robot can halt the entire production line, leading to increased operational costs. These unexpected downtimes can result in losses of up to $10,000 per minute. When industrial robots were first designed, they operated within a closed local network. Programmers would write the robot programs and the operators would debug them on-site. However, with the increasing openness of industrial environments, industrial robots are now being integrated into enterprise networks and even the Internet. Network users are expected to interact with robots through open interfaces. While this trend has improved real-time communication between users and the robots, it has also disrupted the securely closed environment. Industrial robots often lack robust security mechanism to defend against cyber attacks in the open environment. Adversaries can exploit this network interface as entry points to access the robot controller. Once inside, they can leverage potential vulnerabilities in the controller to launch attacks, causing significant damage. Currently, the most popular network interface in the REST API is lightweight, flexible, and convenient design for managing and accessing web resources has made it the preferred choice for industrial robot network interfaces. REST stands for Representational State Transfer. In REST architecture, data and functions are treated as resources, which can be accessed using uniform resource identifiers. Client and server exchange resources through standardized interfaces and protocols. HTTP is the most commonly used protocol. Third-party services or networks users act as clients and send CRUD requests. CRUD is create, read, update, and delete the server. The server processes these requests, performs the necessary actions, and then responds, typically with a JSON payload. A REST request is constructed with the following components: the operation endpoint, parameters, and handlers. For example, in the bottom graph, the operation is get, the endpoint is RW repeat symbol, and so on, with two parameters named symbol URL and value. REST provides a set of guidelines and controls for developing applications. It also comes with a standardized documentation known as the OpenAPI specification or Swagger specification that tells the users how to interact with REST APIs. The OpenAPI specification is typically stored in YAML or JSON fields, which contain information about the API endpoint, available CRUD operations, input parameters, response descriptions, and more. In industrial robot, REST API server has a powerful interface. External requests can directly access the robot controller through REST API, enabling control and programming of the robots. This includes tasks like accessing and modifying files, reading and setting I/O signals, reading and modifying robot programs, and much more. Despite these powerful capabilities, security mechanisms are often lacking, and when security issue occurred, the consequences can be severe. Since external requests directly interact with the robot controller, they have a real impact on the physical space and directly affect the robots in the field. Given these powerful functionalities, we have some security concerns. Are there any flaws in the implementation of the REST service? For example, could there be mistakes or potential vulnerabilities introduced during implementation? Second, has the system been thoroughly tested for security to ensure its reliability? And are there proper checks in place to validate the range of the request parameters? So to address these concerns, we conduct tests on the REST service of industrial robots to identify potential security issues. We focus on detecting bugs that could trigger internal server errors and vulnerabilities that could lead to a denial of service, causing the robot to shut down. However, performing efficiency detection comes with three major challenges. First, how do we generate high-quality test cases? The main goal of testing is to explore the different states of the server at various depths. Therefore, a key challenge is ensuring that the input parameters in the test sequence are correct so that the server can process external requests effectively, allowing us to test its deeper states. Second, how do we achieve high throughput testing? The testing space for REST API is vast, and sending a large number of requests to the server in a short time can consume significant resources on the controller. Since the robot controller is an embedded device with limited resources, they have strict session management and request limits. So executing a high volume of REST requests in a short time is really a challenge. Finally, how do we detect abnormal states in the robot? Robots are typically several physical systems. Its physical abnormal states is difficult to be observed by the program. So we aim to provide a high throughput black box testing tool for industrial robot REST service to uncover flaws in robot controller. We have three key motivations to help us achieve this. Firstly, each operation parameter in the OpenAPI specification may include a description field, which often contains valid examples of parameter values. This can be used to generate high-quality test cases. For example, the text circled by the green box in the graph can be used as the value of parameters. Next, we found the session resources are susceptible to hijacking. We can implement an active man-in-the-middle forwarding mechanism to bypass resource limits. Finally, since the robot controller is a physical entity with clear on-off previous states, we can use this as physical space anomaly indicators. Based on these motivations, we built a prototype system called RoboRest, which consists of two stages and four modules. In the pre-processing stage, we use a parsing module to analyze the OpenAPI specification documents, extracting dependency relationship and parameter information. In the fast testing stage, we force the user generation module to create test cases based on the information extracted in the pre-processing stage. These cases include both single requests and sequences of multiple requests. Next, a forward module is built between the testing client and the server, enable us to bypass resource constraints on the controller and perform high throughput testing. Finally, we observe the state of the industrial robot controller using both cyber and physical indicators to detect anomalies. When the controller triggers a denial of service condition, we conduct post-processing to reset the controller and support automated testing. The first step in our approach is to pass the OpenAPI specification to extract two key information, a dictionary of parameter values, and three types of dependency relationships. For building the parameter dictionary, we extract useful information from the description fields of each operation and parameter in the specification. These fields may include valid parameter values, and the operation description fields provide the information applicable to all parameters within the operation, and the parameter description field offers the detail specific to the current parameter. For example, as shown in the image, the blue section of the post operation contains some simple values, such as TPFK1, TPFK2. We extract all parameter value name from the endpoint and perform knowledge extraction on the description field to identify possible values for each parameter. Similarly, for each parameter's description field, such as the green section, we directly extract possible values from the description and use them to build a candidate dictionary for current parameter. And we use a large language model as knowledge extraction tools for this task. We also identified three types of dependency relationships. First, CRUD relationships. This describes the order of operation for the same schema. For example, a create operation should precede read, update, or delete operations, and a delete operation should come last. Second, schema relationships. If an attribute P1 is one schema S1 is equivalent to an attribute P2 in another schema S2, it indicates that the two schemas are related. Thirdly, if a resource in the response of API A is used as an input parameter for API B, then we say that B depends on A. In this case, A is called the producer and B is the consumer. We refer to this producer-consumer relationship as a data flow dependency. Next is the generation module, which handles two key tasks: sequence generation and request construction. Based on the three types of dependencies, we generate appropriate request sequences. For instance, as shown in the graph, both API use the same schema, OP mode. In this case, the GET request acts as the producer and must be executed before the POST request, which is the consumer. So we can obtain a request sequence, get RW panel OP mode, and post RW panel OP mode acknowledge. After generating the request sequence, we need to provide input parameters for each request to ensure it can be processed by the server. REST assigns the values to input parameters based on these rulers. First, if the request has been successfully executed before, we reuse the parameter values from the last successful run. Second, if the parameter exists in the dictionary we built earlier, REST randomly select a value from the dictionary corresponding to the parameter name. Thirdly, if the parameter for one operation depends on the response of a previous operation, we wait for the early operation to complete and retrieve the required value from its response. Otherwise, if none of the above applies, we assign the random value as the parameter value. For typically REST service deployed on cloud platforms, the previous steps are sufficient for fast testing. However, robot controller imposes strict resource usage limits. They reject excessive requests in a shorter period, and if overloaded, they refuse to accept any new requests. This drastically reduces test efficiency. We discovered that the server performs two types of checks on incoming requests. First, legitimacy check. This ensure requests include valid authentication. Second, resource quarter check. This verifies that the session ID is in the request doesn't exceed the maximum limit. To bypass these constraints, we use a forward module. This module modifies the request date and reuses the session ID from the first successful request to construct subsequent request handles, effectively bypassing the resource quarter check. Specifically, we use a sniffing message with correct functional fields and authentication information to establish a connection with the robot service. Once connected, we record the server's response and reuse session information for all subsequent requests. The last module is robot monitor. We use two types of metrics, cyber and physical, to detect abnormal states in the robot controller. For the cyberspace, just like other REST testing tools, we rely on the HTTP status code to identify server-side internal errors. For the physical space, when the robot controller becomes unavailable, the robot typically enters a closed state. This closed state serves as an indicator of an exception. But this physical state change happens in the real world, where it is something a human observer can spot with their own eyes. A program can't directly detect it, so we need to translate it into a program readable signal. To achieve this, we use other program events that happen at the same time. Here is a key insight. The controller is actually a Windows-based system, and during this process, Windows socket errors are generated. Using specific socket error codes, like a connection aborted or connection reset, we can automatically detect when an error occurs. Finally, during tests, if we find vulnerabilities that lead to a denial of service state, we need to restore it to a normal state to continue testing. To do this, we documented every step required to restart the controller, including the UI buttons that need to be clicked. Then we use AutoIt to simulate mouse clicks and reset the robot. To evaluate progress, we pose the three key research questions. First, how much does the robot improve flaw detection efficiency compared to existing work? Second, how much does the robot improve API operation coverage compared to existing works? Third, how effective is our parameter candidate dictionary in detecting flaws? We conducted experiments on ABB's robot web service. Each experiment lasts for 12 hours and was repeated 5 times. For research question 1, robots identified 19 flaws in total, with 2 vulnerabilities receiving CVE ID. Compared to existing tools like Morris and Zip, our approach detected 9 and 13 additional flaws. In addition, 4 vulnerabilities were discovered through physical states. For research question 1, robots achieved a 30.94% improvement in API operation coverage compared to the state-of-the-art tool. It also detected 90% more flaws. To validate our dictionary strategy, we conducted ablation experiments with 3 RoboRest variants. They are removing all dictionaries and removing only one dictionary. The result of clear combining both operation and parameter descriptions led to the highest success rate for API requests and uncovered the most flaws, where parameter descriptions provided more usable values than operation descriptions. Both were essential for maximum coverage and flaw detection. Okay, to wrap up, Let me summarize our work. We conducted the first systematic study of system flaws affecting the availability of industrial robot REST service. We developed an automated testing tool called RoboRest, capable of detecting bugs and vulnerabilities in robot controller REST service. When applied to ABB's RWS, RoboRest uncovered 4 vulnerabilities and 15 bugs, and we responsible disclosed all these flaws to the developers and obtained their confirmation. Our work can have a serious impact on the real world. The vulnerabilities when discovered exist into mainstream industrial robot controllers. Exploiting these vulnerabilities could affect nearly all ABB industry robots, leading to denial of service attacks and significantly disruption in production processes. Okay, thank you for your attention, and I'm happy to take any questions.
Hello? Yeah. Okay. Are there
Hello?
questions? Okay. Hi. So maybe let me ask a question. So among the kind of bugs that you discovered, was there some kind of a pattern to these bugs that you found? Like, I mean, was it more correlated? Was it more useful to use the parameter dictionaries or the other kind of dictionaries to uncover these bugs?
Oh, sorry, can you repeat it? I don't understand.
I was wondering if there was some pattern to the kind of bugs that you discovered and the vulnerabilities. Uh, did you find one of the two approaches that you presented, and then in the ablation study? Uh, do you have a sense of which of those approaches is more effective at finding the bugs?
Oh, sorry, my spoken English is not good, and I don't understand the last words.
Maybe let me simplify the question. I'm just curious to know if there was some pattern to the kind of bugs that you found.
You mean the evaluate object?
Yeah, I mean, in the last slide, you had like a list of vulnerabilities and bugs. So was there some kind of common pattern among them, or they were all kind of different?
Uh, those last my last slide.
Yeah, in your experimental results, you showed that there were some vulnerabilities and some bugs. Uh,
Uh,
cou- I mean, is there some kind of a pattern that you found that was common among those?
I think maybe they're not.
Okay. Any other questions? Okay, then in that case, we thank you for the talk and thank you for attending remotely. And that concludes the session for today.